Hello everyone, I hope you're all doing well. We're going to be solving one more problem on particle kinetics, and this is going to be in the curvilinear coordinate system. Okay, so we're going to solve a problem on kinetics. So curvilinear kinetics. Which means that typically the motion is not along a straight line path, it's going to be along a curved path. And very nice problem. This is a foundational problem, so I want to write this down. Okay, so foundational problem in dynamics. Okay, and what is that foundational problem? The foundational problem is obtain the equation of motion. Okay, so obtain the equation of motion of the pendulum system shown below. Okay, key word here is equation of motion. I'm pretty sure that this is something that you may not have come across. Okay, equation of motion of the pendulum. Okay, the pendulum system is one of the foundational problems in dynamics, because the pendulum is a representative of many things that can be modeled, many real things that can be modeled using the motion of a pendulum. So the human body is an example of a pendulum system. It's almost like an inverted pendulum that every day we are walking, and we kind of rock back and forth as we walk, and the motion can be captured by means of looking at it as an inverted pendulum. And you got to understand how much of a feedback loop there is in our mind, that our motion of walking for a normal human being is a very stable walk. Okay, so this is in that sense a foundational problem. Okay, so what's a simple pendulum? I'm pretty sure that is known to most of us. Okay, so here is an example of a simple pendulum with a fixed pivot. Okay, so here is called the pivot of the pendulum. So this is the pivot. In this case, it's a fixed. And a pendulum is nothing but something. I take a string and then I attach it to this one, and then at the end of this string I attach the bob of the pendulum. Okay, so that's essentially a pendulum for me. I want to make it slightly larger, but not too large to make it a rigid body. Okay, so this is called the bob of the pendulum. Okay, this is the length L, or the string of the pendulum. Okay, that's the length of the pendulum. So this is the pivot, then I have the string of the pendulum, and then I have the bob of the pendulum. Okay, and at any point in time, let's say that the equilibrium position of the pendulum was this vertical location. So I'm going to write it down. Okay, so this is going to be as a dotted line. Okay, so this is the equilibrium position of the pendulum. I'm sorry, equilibrium position of the pendulum. Okay, and then the pendulum has been disturbed from its equilibrium position by means of maybe an initial displacement or an initial velocity, and we'll talk about these in greater detail. Okay, so here are some of the assumptions in this problem. Okay, so assumptions. First thing, no external forces other than gravity. Okay, the bob of the pendulum has a mass m, and the string of the pendulum of a length little l. Okay, so the assumptions are the no other external forces other than gravity. So the question is, how the hell is this moving? right? It is moving because of some initial conditions or initial displacement. So which means that in the absence of external forces, the pendulum is set into motion by either an initial displacement or initial velocity, or both. From its equilibrium position, Okay, so this is how the system is actually set into motion. Okay, the other thing I'm going to assume is that the string is massless. Okay, and I'm also going to assume that the string is inextensible, massless and inextensible. Which means that the length of the string remains a constant. Okay, so length of the string is equal to a constant. Okay, so there are no external forces other than gravity, which means that the pendulum was initially in this vertical position and then somebody has come and disturbed it. Okay, so this is called as an initial disturbance. Or an initial perturbation. Okay, so that's another word for it, an initial disturbance, or it's also called as an initial perturbation. So, or an initial perturbation. Okay, or more fancily called as initial conditions. Okay, so it can be both initial displacement and velocity, or just one or the other. Okay, that's good enough for us. All right, so these are the assumptions that are involved in the problem. You know, whenever I start any problem, you've got to have some assumptions. So list out all the assumptions. Okay, then what I'm going to do is, before I go ahead and talk about what is exactly meant by an equation of motion, I have to talk about other things. Okay, so let me first look at what are called as the configuration coordinates of the problem. Okay, so what are the configuration coordinates? So the basic definitions. These are necessarily, or may or may not be, terms that you may have come across in your physics classes, but here is what we have. Okay, so from the point of view of a basic definition, I have a configuration coordinate. Let me write that F properly. Configuration coordinates are the total number of coordinates required to specify the position of the particle at any instant in time. Importantly, in the absence of constraints. Okay, so this is the definition of a configuration coordinate, and we will look at this from the point of view of our problem, okay, which automatically leads us to thinking, okay, what are constraints? Okay, constraints are typically restrictions on the motion of the particle. Okay, so these are restrictions imposed upon the motion of the particle, upon the motion of the particle. Okay, so this is meant by a constraint. And the last thing that I want to define here before we go ahead and look at our problem is called degrees of freedom. Okay, degrees of freedom, or I'm going to call them as DOF, okay, shorthand notation. These are the important with the minimum number of independent variables required to specify the position of particle at any time instant. Okay, so a couple of important things going on here. Okay, these are all new terms that we are coming across the first time. So minimum number of independent variables, okay, that are required to specify the position, okay, of the particle at any point in time. Okay, there is an equation, a nice equation. The degrees of freedom is equal to the number of configuration coordinates minus the number of constraints. Okay, so degrees of freedom are the number of configuration coordinates minus the number of constraints. This is a foundational equation in dynamics. Okay, so what are configuration coordinates for our problem, and how are they different from the degrees of freedom, and what are the constraints for our problem? Okay, so I'm going to go back to our problem. So back to our problem. Okay, and I'm going to bring back my pendulum. This is a problem that I really love. Pretty much you'll see me bringing out a pendulum problem whenever I'm bored. Okay, alright, so here is our pendulum system. Okay, it's a fixed pivot, length of the pendulum is known, and so on and so forth. So for us, we will start off by writing out the configuration coordinates. Okay, so configuration coordinates. Let me write that properly. Okay, so typically we are doing this as a two-dimensional problem, so 2D or planar problem, which means that what I have to first think of is this. Okay, in the absence of a constraint, okay, in the absence of constraint, which means that the string, you see the string is the constraint, right? This is, the string is essentially telling this particle or this pendulum, hey, don't move this way, you got to move only in a certain way. Okay, you cannot snap off and come off of me. Okay, so the string is the constraint. In the absence of a constraint, if I set up an XY coordinate frame right here, okay, so if I set up this as my Y coordinate, and let's say, so this is my Y coordinate, and here is my x-axis. Let me scoot this over a little here. Okay, so here is my x and y coordinates. So in the absence of any constraints, I need to specify x of t, y of t, to know where the particle is, to know where the bob is. And you agree with me, right? So which means that, you know, at any point, if this string were not there, this is essentially a particle in space. That is, if the string were not there, the bob would be a particle in 2D space. Which means that, you know, if I have to specify its position at any point, I need 2 configuration coordinates, which means that the number of configuration coordinates is equal to 2. Okay, then immediately, what about the constraint? The constraint is the string of the pendulum, right? The string is of a fixed length. Okay, so a fixed length string prevents the particle from doing whatever it wants to do. Okay, so constraints motion of the particle to be along a circular path. Of a constant radius. Equal to the string length. And this implies that, you know, there is no slack in the string. Okay, so implies no slack in the string. Okay, so that's something that is implicit. So which means the number of constraints for us is equal to 1. Okay, so the number of constraints is equal to 1, which means that for me, the number of degrees of freedom is equal to, and I wanted to make a note of it, this has to be the number of degrees of freedom here. So maybe before I go ahead and do something else, so let me do this here. Need to bring these creatures. Why not make it straight, right? Since I'm already here. This is the number of degrees of freedom. Okay, so the number of degrees of freedom is equal to number of configuration coordinates minus the number of constraints. I'm just going to copy this. I'm going to keep writing this again and again. Okay, so the number of configuration coordinates minus the number of constraints. I need to copy. I'm sorry. I need to do that here. Okay, so which means that for me, the number of degrees of freedom is equal to 2 minus 1, which is equal to 1. Okay, so in our problem, it is not easy to identify degrees of freedom. So which means for us, what is the degree of freedom? For us, if I know only one variable, I know the position of the pendulum at all points in time. So which means we have to think. So think. If I know just one variable, that will tell me where the bob is at any point. And importantly, when I say just one variable, just one independent variable, I mean just one independent variable. What will that be? Okay, if I go back to my figure here, you obviously see that the choice is going to be theta, because if I know theta, I know the length of the pendulum is always a constant. So if I know theta, I know L, I know the position at any point in time. Okay, so this is going to be theta. Okay, so which means that the degree of freedom is theta of t. That is, if I know theta of t, and since I know length L given, we can obtain the position of the bob at any time instant. All right, fantastic. So this is the key thing that we have found out here, that theta, the degree of freedom, is theta of t. For me in this particular problem, the number of degrees of freedom is equal to 1. Okay, the number of degrees of freedom is the configuration coordinates minus the number of constraints. Then I finally come to the last definition of our setup here. So I'm going to define the equation of motion. So equation of motion and this is the another foundational principle of dynamics, is the following. Not principle, foundational term in dynamics is equation of motion. Equation of motion, which I'm going to call as EOM. Okay, so equation of motion is in dynamics. Okay, in dynamics, equation of motion is a second order ordinary differential equation written in terms of the degree of freedom variable. Okay, so this is the definition of equation of motion. How is the equation of motion obtained? From the laws of mechanics. Okay, so equation of motion is obtained from laws of mechanics. Okay. And what are those laws? Newton's laws, typically Newton-Euler equations if you're going to go to the rigid body motion. Okay, so which means that our expectation is to expect a second order ordinary differential equation, which I typically call as an ODE. Okay, second order ODE in terms of theta. Okay, and that's exactly what I'm going to be doing. Okay, so to understand the motion of the pendulum, since it's going along a circular path, okay, so since the pendulum moves along a circular path, this is going to be motion along a curve, which means that I need to choose either radial transverse, or I need to choose the normal tangential system. I'm going to be choosing the radial transverse, and I'm going to be having you solve for the normal tangential in a particular homework problem. Okay, and then you'll see the answer is going to be the same thing, of course. Okay, so I'm going to take the pendulum system. Okay, so here is my figure from before. Okay, so I'm going to copy that, and I'm going to say, okay, hey, I'm going to set this up here. Okay, I'm going to choose a radial transverse system. Okay, which means that for me, I'm going to be sitting here as a fixed observer. Okay, so first of all, I position myself as a fixed observer. Okay, and I'm going to say, okay, this is the point O. So O is a fixed observer. Okay, and then from the perspective of O, I'm going to be drawing the radial unit vector towards the particle. Okay, so which means that that's going to be in the direction here. That's going to be my radial unit vector, E suffix r. and then my transverse unit vector in the direction of increasing theta. Okay, as you can see, the pendulum, I'm assuming it to be swinging counterclockwise, so this is going to be in the direction of increasing theta. Okay, direction of increasing theta. Okay, so theta is a degree of freedom. Okay, and I immediately know that, okay, this length is a constant. Okay, so here I can say this is r of t. Okay, r of t. So with respect to the fixed observer O, okay, so the position vector of the bob is going to be r, which is going to be r times er or L times er. Okay, and so I can say that from kinematics, we know that the velocity vector in the radial transverse coordinate frame is going to be r dot er plus r theta dot e theta. Okay, but for us, r of t is going to be L, which is a constant, which means that r dot is going to be 0. And this also implies that r double dot, if you're going to look at acceleration, is going to be 0. Excuse me. So which means that the velocity is going to be 0 er plus L theta dot e theta, or velocity is L theta dot e theta. Okay, so this is the velocity of this particle. I'm going to call this as particle P, that is the observer O, and I'm going to write this as rp slash O. Okay, and this is velocity p slash O. So look at this. So rp slash O is r er. This is the position of the bob P as seen by a fixed observer O. Okay, velocity p slash O is L theta dot, or LER if you want. Okay, so I'm going to cut that off and write that as LER, L theta dot E theta. This is the velocity of the bob as seen by a fixed observer. I'm just going to copy that. Okay, this is the velocity of the bob as seen by a fixed observer, and in this situation, this term VRPO and VPO, okay, they're called as absolute position and absolute velocity. Absolute position and absolute velocity, since they are with respect to a fixed observer. Okay, that is the important thing here. Okay, so I'm going to underline that. So that's a fixed observer. These are called as the absolute position and the absolute velocity vectors. And likewise, I can go back and look at the acceleration. So acceleration is, by basic definition, r double dot minus r theta dot square, and 2 r dot theta dot plus r theta double dot. I'm going to cancel off some of these terms. R double dot is going to be gone, r dot is going to be gone here, so which means that I'm going to say that for us, acceleration of P as seen by the observer O is going to be minus L theta dot square ER plus L theta double dot E theta. Okay, so this is a very, very important thing. This is also, once again, the absolute acceleration. So this is also the absolute acceleration of the particle P. Okay, then here is what I do. Okay, so this is all the basic kinematics here. Now I draw the free body and the kinetic diagram. Okay, So next step is draw the FBD and kinetic diagram. Okay, this is our first problem in curvilinear coordinates, so I'm going to take my time doing it. So this is step number 2. Okay, I'm going to call this step number 2. First is do some kinematics. Okay, so first step is kinematics. Okay, that was in the radial transverse coordinate frame. And then we come to drawing the free body and the kinetic diagram of these quantities. Okay, let me scoot that down a little bit. So how do I draw the free body and the kinetic diagram? It's fairly straightforward. Okay, I bring this creature once again. So here is who I have. Okay, so I just paste that here. So this is the actual figure. Okay, so here's what I'm going to do further. I'm going to cut this figure off, and then I'm going to copy that, and I'm going to take that and paste it 2 times. Okay, one for the free body diagram, one for the kinetic diagram. I'm going to cut that off. That's a particle. I'm drawing the free body diagram of the particle, okay, which is quite obvious, I hope, of the bob P. Okay, so first of all, what am I going to have? I'm going to have a tension in the cable. Okay, so this is the tension that is in the cable, that is going to be along the radial direction, so I'm going to call it as T. Then I'm going to have the weight of the bob, which is acting vertically down. Okay, so this is the weight of the bob, which I'm going to call as W, which is M times G. Okay, and you can take the weight and then take it up and break it into components. Okay, so if you look at the components, so this angle is also going to be equal to theta. Okay, which means that if I look at the components of the weight, then I'm going to have one component which is acting this way, so that's going to be mg sine theta. And then I'm going to say that, okay, there is one more component of the weight which is acting in this direction here, which I'm going to call as mg cos theta. Okay, so I'm just taking the weight and breaking it up into its components. And if you want, you can scoot this weight down here. So typically you can draw that here if you want. So maybe let me redraw my figure with the weight shown here. Okay, so this is W. Of course, I got to get rid of some of these terms here, which are going to be a little hard to do. Let me try my best. Okay, that doesn't let me do it, but let me take this and bring these terms here. Okay, so that's mg sine theta here. Then I need some arrows. Okay, so that's mg cos theta and mg sine theta. Okay, so this is the free body diagram. So this is the FBD of the bob P. Okay, I hope this is fairly clear. All I did was take the weight and I drew it down. Okay, so that's the angle theta that you had there. Now what do I do in the kinetic diagram is I carry along with the same procedure. I say, okay, in the kinetic diagram I don't draw the tension or anything. Along the E theta direction I draw mass times acceleration in the E theta direction. So mass times acceleration in the theta direction. Along the ER direction, which is what I've chosen as the positive ER and positive E theta, mass times acceleration in the R direction. And this is going to be the kinetic diagram of P. And as a clue, what is this guy here is going to be AR, and this is going to be A theta. Okay, so which means that AR is going to be minus L theta dot square, and then A theta is going to be L theta double dot. Okay, we're almost there. Then all I have to do is the following. Okay, so start summing forces up. Sum of forces in the radial direction on the free body diagram with this as the positive radial direction is equal to sum of forces on the radial direction in the kinetic diagram with this as the positive radial direction. What are the forces? I'm going to have T, which is negative, right? Because I'm saying things pointing down are positive, so this is going to be mg cos theta minus T is equal to m times AR. Okay, so this is equation 1. And then likewise I'm going to say, okay, sum of all the forces in the transverse direction on the free body diagram is equal to sum of all the forces in the transverse direction on the kinetic diagram. And I'm going to say, okay, this is the positive transverse direction, as you would have seen. Okay, so which essentially tells me the following. What are the forces? I'm going to have minus mg sine theta, okay, and this is going to be m times a theta. That is equation 2. Okay, now where is the equation of motion? Let me first write out these equations carefully. From 1, I have tangent T is equal to mg cos theta minus mar, or the tangent T is mg cos theta minus mar. Okay, look at ar was minus L theta dot square, so that's going to be m times minus L theta dot square, which means that the tangent T is mg cos theta plus ml theta dot square. Okay, so that is the first thing that I have. Then from equation 2, we're almost there. From equation 2, I'm going to see that ma theta plus mg sine theta is equal to 0. I'm just rearranging the equations. And then look at a theta, that's going to be m times L theta double dot plus mg sine theta is equal to 0. Or I'm going to say, okay, cancel off these common terms of the mass and then take the length and then divide it through. I'm going to get theta double dot plus g by L sine theta is equal to 0, or theta double dot is equal to minus g by L sine theta. You are now looking at probably one of the greatest equations in dynamics. Okay, this guy here is called as the equation of motion. I'm going to label them as equation 3, equation 4. Okay, so equation 3, which is T is equal to mg cos theta plus ml theta dot square. This is called as the constraint equation. Okay, and then equation 4, which is theta double dot is equal to minus g by L sine theta is called as the equation of motion. Okay, these are the key things that we were asked to find in this problem, and I just want to clarify a couple more points before we call it a day on this problem. So note, equation of motion, which is this guy here, is a second order ordinary differential equation in terms of the degree of freedom, which is theta of t. Okay, it's a function of theta, right? The second thing, equation of motion should never contain the constraint force. Okay, this is a key statement. Okay, so my should doesn't look too great, so I'm going to rewrite that. Should never contain, okay, should never ever contain the constraint force in there. Okay, so if you look at my equation of motion here, this equation of motion does not contain the constraint force. The constraint force has its own equation here. Okay, so the equation of motion does not contain the constraint force. Okay, and typically the third step is, okay, upon solving equation of motion, we can obtain theta of t at any point in time. We are not going to be doing this, not do it in this course. Okay, you will typically use maybe techniques of differential equations, or you'll use techniques that you learn from numerical methods. One thing I want to mention here is that so for us this is the equation of motion. Okay, and I'll bring that down here. Very last step, this equation of motion is a nonlinear ordinary differential equation here. So for us, for our problem, because of the presence of sine theta, the equation of motion is non-linear. Okay, which means that the solution is going to be fairly difficult, and so mostly the solution is obtained by means of numerical methods, which I'm sure you have taken numerical methods class, or probably taking it currently. So those are the techniques that you're going to be using there. Okay, so just as a very quick recap, okay, I'm just going to go back very quickly to some of the terms of importance. Okay, configuration coordinates for our problem was x and y. Okay, this was in the absence of constraints. But typically, equation of motion is not in terms of the configuration coordinate. Equation of motion is in terms of the degrees of freedom. So what are the constraints for us? The constraints are that the length of the pendulum is fixed. Okay, and so then if the length of the pendulum is fixed, I have two configuration coordinates. I come up with the number of degrees of freedom, which is equal to 2 minus 1, which is 1. It is not easy to identify the degree of freedom. But then we think and say, okay, how do I find out the degree of freedom here? I need only one independent variable. Okay, the key word is one independent variable, which will tell me the position of the entire pendulum bob at any point in time. Okay, which means that this is going to be theta as a function of time. Okay, so the degree of freedom is theta of t. If I know theta of t, then I know where the bob is at any point in time, because I know what its length is. So then I go and say, okay, how do I find this theta of t? To find the theta of t, I need to solve for the equation of motion. How to find the equation of motion? I need to solve using the laws of mechanics. Okay, so basic flow rule, essentially, if you want to think of it this way. Okay, so basic steps overview is to know the motion of the bob, we need theta of t at any point in time. To know theta of t at any point, we need to solve the equation of motion. To know equation of motion, we set up the FBD and the KD and perform force balance. And so you see the logical process, right? So, and to do these kinds of things, we need to identify what the degree of freedom is and so on. So to identify the degree of freedom, we see what the constraints are, what the configuration coordinates are. We got to do this for each and every problem in front of us. Okay. So thank you for your patience. These lectures are going to get slightly longer, but I hope this is worth the effort and the time that we are putting in. Thank you, and take care of yourselves.